Welcome. In this lesson, we're going to be looking at graphs in terms of linear approximation, real-world problems, and determining whether our approximation is an underestimate or an overestimate. As a reminder, the linear approximation model, L of x, equals f of a plus f prime of a times the change in x. And essentially, this is just the equation of a line, right? In sort of a modified slope-intercept form. F of a is the point that you're using to do the approximation with. It's the point whose tangent line as an approximation of the function, right? And so it's, in other words, it's the nice value. It's the nice nearby value. This is just the slope of the tangent line. It's the nice nearby value that the tangent line is going through because we're using that particular slope, right? So since it's that slope, it's that value. And then this is the change in x. All right, so let's take a look here at our graph. We're going to use this graph to do some approximating. And we see in some places this graph is concave up. Like right here, this graph is concave up. And in some places it's concave, we see some places this graph is concave up, like right here and right here. And some places where it's blue, the graph is concave down. Right? So right here it's concave up. Here it's concave up. And here it's concave down. All right, so let's use our graph here to approximate, estimate some values. Let's use, so let's approximate the value x equals negative 0.1. And let's also use the value, well, I don't know how interesting it'll be, but I want something that is probably a little bit more than 3. So let's use the value 3.2. All right, so we'll use those two values. This is the graph of y equals cosine x. We can see the tangent line. You can almost draw through it. I'm a little bit too high. Right there's our tangent lines. Okay, so there, my graph's too high too. Let's just move the whole thing. Right. So now we need a value that's nice. That's near to negative 0.1, but nice. How about 0? That one's a good value. All right, so our function here is f of x equals cosine x. All right, so f of 0 is cosine 0, which is 1. We need the derivative. Right, so the derivative of cosine x, of course, is negative sine x. And pretty easy to evaluate the derivative. Negative sine 0 is just 0. And our change in x is going to be negative 0.1 minus 0. Right? We would expect it to be, well, we'd have to take off a little, right? Because we're evaluating for a smaller value. All right, so now let's use our linear approximation method. So f of negative 0.1 is approximately, right? So f of a is 0. Actually, maybe I'll write it in as that. I'll write it in as f of 0 plus f prime of 0 times the change in x. Right? And so that would be 1 plus 0 times negative 0.1. Well, that's just going to be 1. And we see from our graph, I don't know, it's about maybe, I have to estimate, maybe here. It's pretty close to 1, right? It's not exactly 1. It's actually a little less than 1. Our approximation here is an overestimate. Because our graph is concave down, our approximation is an overestimate. So let's write that in. So f of negative 0.1 is an overestimate. Since f of x is concave down, near x equals negative 0.1. Let's do this exercise again, but this time x is going to be 3.2. What's a nice value near 3.2? Well, pretty nice value would be pi. Pi is pretty close to 3.2, and a lot easier to calculate with than 3.2. At least if I'm not using a calculator, that is. All right, so I'm going to plug that in. Oops, there's my calculator. I'm going to have to get an approximation here for the change in x. Actually, I'll do the rest of it, and then I'll do the change of x. All right, so f of pi is just going to be cosine pi, which is going to be negative 1. And, of course, the derivative, again, is going to be negative sine x. If we evaluate that, we have negative sine pi, which is also 0. And now we just need our change in x. So the change in x is going to be 3.2 minus pi. So now I'm going to use a calculator so I can get a better estimate than just 3.14. All right, so 3.2 minus pi, which I'm trying to hold the calculator and the microphone at the same time. I don't know what I did, but I didn't do 3.2 minus pi. So it'd be 0.0584. I'm going to turn off the calculator. It's kind of dying. Did I say 0.0584, right? Yes. All right, so now we have all of our parts. All right, so now we can use our linear approximation method. And so, where can I squeeze this in? Right here. F of pi is approximately, I won't write it out. It's the same as this. All right, I don't have enough space. Except it's going to be f of pi plus f prime of pi times the change in x. All right, but otherwise it's the same as that. All right, so that would be negative 1 plus 0 times 0.0584, which is just going to be approximately negative 1, or equal to negative 1. The approximation is approximately negative 1. That calculation is exactly negative 1. All right, so again, so here would be a little bit right about there. All right, we can see that that's not going to be as low. Pi's got to be right here, where you've got that relative minimum there. So you can see it's a little bit more, right? It's a little bit more than or it's not quite as small, right? It's a little bit more. All right, so right there we are concave up. So since we're concave up, we have an underestimate. We've underestimated our value. Right? We should be a little, right? We shouldn't be at -1, right? We should be a little bit more than that, right? -1. It's kind of hard to think of it because we're negative. So -1, right, is even less, right? We've overestimated because we're not as low as -1, right? So we can say that f of, what was it, 3.2 is an underestimate since f of x is concave up. Near x equals 3.2. Right? So we're really not as small as -1. We're a little bit more. So we've underestimated, because -1 would be smaller than where we really are. We're probably at like maybe -0.8, right? Something like that. All right, so we can determine whether our estimate is an overestimate or an underestimate simply by knowing whether the function is going to be concave up or concave down for values near where we're estimating. Okay? And it helps if we have a graph or can calculate out a graph. All right, so if f of x is concave up, it's going to be an underestimate. How I remember that? Well, you can think about it logically, or you can just think up, under. Right? And because we're using a smaller value. And if it's down, it's over. All right, so here we have a graph. Suppose the only information we have about a function f is that f of 2 equals 3. And that the graph of the derivative of f is shown at right. So this is the graph of f prime of x. Use a linear approximation model to estimate f of 1.9 and f of 2.1. And then B are your estimates over or under estimates. Right? So I don't know if I have enough space there. I'll start it up here and then maybe I'll use an arrow or something like that. All right, so we'll do 1.9 first. All right, so x here is 1.9, not very nice. To calculate what's close to 1.9, that would be easy to calculate. Well, 2 is pretty close to 1.9, and we know that f of 2 is equals 3, so that was no problem at all. Right? And now we need to find out the value of our derivative. Right? So we need now f prime of 2, right, for the slope in our linear approximation model. Well, now we just have to go over just as we have the graph of the derivative. So if we follow up 2, kind of interestingly, f prime of 2, excuse me, is 3. Then that's just a coincidence. All right, so we have f of a, we have f prime of a. All we need is the change in x. All right, so that's going to be 1.9 minus 2, which is -1/10. All right, so now I'll just put it up here and then I'll do the other value below. All right, so our linear approximation model, I'll just use f. f of 1.9 is going to be approximately, it's going to be f of 2 plus f prime of 2 times the change in x. So that would be 3 plus 3 times -1/10. So that would be 3 minus 3/10. well, that would be 3 is 30 tenths. So that's going to be equal to 27 tenths. All right, so we calculated out the first one. So 1.9, using the graph of our derivative and what we know about our function, is approximately 27 tenths. Let's do the same thing. But now x is 2.1. A is still 2. F of 2 is still 3. F prime of 2 is still 3. Change in x is the only thing that's changed. So now we have 2.1 minus 2, so that's positive 1/10. So then f of 2.1 is approximately f of 2 plus f prime of 2 times the change in x. Same thing, because we're using the same value. So 3 plus 3 times 1/10, and that's going to be 3 plus 3/10. That's a plus. It still doesn't look like a plus. Which is 33 tenths. There we go. And it makes sense that they would be, we're going up, 1.9 and 2.1 are the same distance from 2, and we're using a linear model. So we kind of expect now we're adding a tenth. All right. The next question asks us to determine, are your estimates in part over or underestimates, and explain. Right? Always get into the habit of justifying. All right, so we have the graph of the derivative here. And something that I notice is that f prime of x is increasing everywhere. And we know that if a function is increasing, its derivative is positive. So if f prime of x is increasing everywhere, then f double prime of, looks terrible. My prime mark is too big. Let's write that again. Then f double prime of x is going to be greater than 0. Now that's not an explanation, but that's getting us on the right path, right? So if that derivative is increasing everywhere, then the second derivative, the derivative of the first derivative, has to be positive. All right, so now let's put our explanation in. All right, so now since f prime of x is increasing everywhere, of course I'm going to use that piece of information. Then f double prime of x, yeah, I'm going to move that down. That's a little crowded there. Then f double prime of x is greater than 0, which means that f of x must be concave up. Right? So if your second derivative is positive, the graph is concave up. The second derivative is negative, then the graph is concave down. Right? So since the graph is concave up, since f of x is concave up, and you can either put everywhere or near our value. If it's everywhere, it's near our value. I think putting everywhere covers it. So if the first derivative is increasing everywhere, the second derivative has to be positive everywhere, and therefore f of x has to be concave up. Since f of x is concave up everywhere, I'll just put the estimate, because it's going to apply to both of them. the estimates, let's put approximations. So I don't have, otherwise I have the estimates are going to be underestimates. So the approximations, although they use the words estimate twice in the question. Approximations or estimates are underestimates. We have underestimated the value because the graph is concave up. All right, and we have this one done. Got a couple more. Suppose you stuff a turkey and then put it in a 350-degree oven. After an hour, the meat thermometer indicates the temperature of the turkey is 89 degrees Fahrenheit. And after 2 hours, it indicates 135 degrees Fahrenheit. Predict the temperature of the turkey after 3 hours. Do you think this will be an overestimate or an underestimate? All right, so let's think about this. So I see the word predict. I want to approximate or estimate. We're going to use a linear approximation method. All right, so we have a starting value. We have some values. We know that f of 1 is 89 degrees, and f of 2 is 135 degrees, and we want to find f of 3. Well, the closest value we have is f of 2, so that will have to be close enough. We know that f of 2, I'll have to write it again. So f of 2 is as close as we have. So the x value that we want is 3. The one that we can work with is 2 because we have a value for that one. We know that f of 2 is 135. Right? Now, we need to know what f prime of 2 is. And we don't have a function. I can't just go take a derivative here. I don't have a function, and I don't have a graph of a derivative where I can just look up the value. So what can I do for the derivative? Well, remember that the derivative, the instantaneous rate of change, can be approximated with the average rate of change. Right? So that means that f prime of 2 is approximately, so the average rate of change is just going to be f of 2 minus f of 1 divided by 2 minus 1. Yeah, I'll just start writing over here now, which is going to be 135 minus 89 divided by 2 minus 1. So that's going to be 46 degrees. So that's going to be, that's approximately, that's the best we can do, is that average rate of change to approximate our instantaneous rate of change. So f prime of 2 is approximately 46 degrees, and we will take it. Now all we need is a change in x. So that's going to be 3 minus 2, or 1. And we have all the pieces. So now what looked like, maybe when you saw that problem, you thought, oh my gosh, that's really hard. I don't know what to do. But using a linear approximation model and approximating our instantaneous rate of change with our average rate of change, now you see this problem's not so bad after all. So f of 3 is approximately going to be f of 2 plus f prime of 2 times the change in x. So that would be 135 plus 46 times 1. And so that's going to be 181 degrees. So now this is assuming, right, with a linear approximation model, we're assuming that it increases the same amount every hour. So if it did, right, that would make sense. Every hour it increases by 46 degrees. That's not really how it's going to work. Right? It's not going to be a nice, pretty straight line. Right? It's going to probably start increasing a little faster as it heats up. When something's hot, it gets a little hotter faster. So do you think this will be an overestimate or an underestimate? Right? So if the temperature is going to keep increasing at a faster rate, probably like an exponential function, the graph probably is going to look like this. Right? Now, if we had another point, we could graph it and get a little bit better of an idea. With 2 points, you graph 2 points, you're going to have a line. So the graph is going to look something probably like that. So our graph would be concave up. Right? Because the temperature will increase faster and faster. If the graph is concave up, this is probably going to be an underestimate. So since temperature, and as long as I justify it, I don't have a whole lot of information to go on here. So since temperature will probably, I feel pretty comfortable saying that, continue to increase at a faster rate, because temperature change actually is not linear. Ooh. I'm going to give myself just a little bit more space. The graph is concave up, and the estimate is an underestimate. Let's try the next one. We have 2 more. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function of time, where t is measured in minutes. For t between 0 and 12 minutes, the graph of r is concave down. The table below gives selected values for the rate of change of the radius over the time interval from 0 to 12 minutes. I can't remember the time unit. The radius of the balloon is 30 feet when t equals 5. All right, so we have some information there. Right, we have f of 5 is 30. Oh, this must be where my glitch is. All right, so what did we want to find? Oh, at 5.4. All right, so we have our x is 5.4. Oops. The value we're going to use is going to be 5, because we know that one, and it's close. F of 5 is 30. How are we going to find f prime of 5? Well, again, we have values here at different times. We can use average rate of change to approximate instantaneous rate of change. Sorry, I had to text my husband, tell me pick him up later. I'm still making a video. All right, so f prime of 5, we're going to use the average rate of change to approximate the instantaneous rate of change. All right, so we want to be around 5. All right, so we're going to use 2 and 7. That's as close as we get. So f prime of 5 is approximately 7 minus 2. Oh, excuse me. We need, I'm sorry. We have, I did not read this graph very carefully at all. We have the derivative, not the radius. All right, so we don't need to approximate. At least it didn't take me long to figure that out. We have it right here. This is not the graph of this is not the table of values for the length of the radius. This is the table of values for the derivative. So here it's a good opportunity for a little lesson. Always look carefully at when you're given a graph or given a table, what it is you're given a graph or table of. All right, I just looked very quickly. I'm like, okay, we've got the values of the radius. Wait a minute. For certain times, oh, wait, that doesn't make any sense. No, we have the values of the derivative. So f prime of 5 is 2. Hopefully you weren't confused for too long. So we have really everything we need except for change in x. So change in x is just going to be 5.4 minus 5. And now we can calculate this out. No problem. So will be approximately f of 5 plus f prime of 5 times the change in x. So that would be 30 plus 2 times 4/10. So that's 30. We can reduce that. Let's see, that would be 4/5, right? All right, and so 30 is 150. This is going to be 154/5 feet. All right, so the approximate radius, excuse me, not radius. Yes, radius. So the approximate radius of the balloon when the time is 5.4 seconds is 154/5 feet. All right, so let's see, do we answer the question? We estimated the radius of the balloon when t equals 5.4. Now that we read the table more carefully, using the tangent line approximation at t equals 5, is your estimate greater than or less than the true value? Give a reason for your answer. All right, let's look at our values for the derivative. Notice 5.7, 4, 2, 1.2, 0.6, 0.5. They're going down, right? That means they're negative. So since f prime of x is decreasing, if a function is decreasing, then its derivative is negative. F double prime of x is going to be less than 0. And therefore, and actually let me qualify that. That almost makes it sound like it's decreasing everywhere. I have no idea what happens after 12 seconds, but it is decreasing on zero to 12 seconds. That makes f double prime of x negative. And if the second derivative is negative, then the function has to be concave down. Let me make sure my sentence makes sense. Since f prime of x is decreasing on t equals 0 to 12 minutes, f double prime of x is going to be negative, and f of x is therefore concave down. Our estimate is an overestimate since f of x is concave down. Almost guarantee there'll be a problem like this on an AP test. All right, and so remember, when you're estimating, think linear approximation, right? And it really is set up the same way each time, right? It's just some things may differ. Where are you getting your information for the derivative? Could it be from a graph? Could it be from a table, right? Or do you have to use the average rate of change to approximate? All right? But here's a nice, we had a couple real good real-world problems to really help you through these. I have only one more problem left. Right? And since my video is a little long, I'm going to end this video, and I'm just going to do the one problem on its own little video. All right? So bye for now.